is heat exchange and thermoregulation kind of concept. So the big picture thing is that we're talking about how these animals maintain body temperature within a range. And why would they do that? Just to get us going again.
Maintain homeostasis.
Yeah, so that process is maintaining homeostasis, but my real question is, why are they doing it?
Maintain protein structures.
Yeah, so that's really specific. So,
Maintain water.
because that, in that range, what's going on?
Metabolism.
That's where they can function
Properly.
Properly.
Most
not
efficient.
properly, most efficiently or best, right? So that range is where things physiologically are happening at its optimal level. I'm gonna talk a little bit later about some other things that organisms have to worry about that might influence that, and it relates to heat exchange. So, but right now, we're just talking about the mechanisms by which these animals exchange heat energy with the environment, thereby maintaining homeostasis, or in some cases affecting what they do. Okay, so the last thing we talked about was infrared radiation. So this one's a little bit confusing maybe, but so we're not talking about the heat, like to the touch, that's emitting from the surface, because that's going to be something different. That's conductive heat exchange. But in this case, we're talking about a different type of energy that comes from the surface of things. It doesn't, even if it's not sitting in the sun. And so these organisms have kind of morphological modifications that limit that part of it, that manage that part of it, the infrared heat radiation. So the main thing is that they're trying to limit the infrared radiation that they're absorbing on the belly, and they do that by having these types of scales which are glossy and that has very high or low emissivity. The scales.
Low.
Low, right? Because that's where the energy is coming from directly. So they want to limit that, because these animals are living in an environment, where heat energy is abundant, right? So they're living in desert environments. And so they're trying to limit the amount of heat energy they're absorbing. One way they can limit the infrared is to have these glossy scales, because the glossy scales have very low emissivity. It's not letting that infrared energy in. The matte scales on the dorsal surface have matte morphology, and that corresponds to high emissivity. So essentially what's happening is these animals are also giving off infrared radiation. If the scales are matte, then or high in emissivity, that infrared radiation can be released through that border. Right? If not, then all that infrared radiation is going to be trapped, and so that's going to kind of exacerbate their problem. So these animals, because they live in environments that are already abundant heat energy, they have to limit wherever they can, and that's one way they can do it. Okay, the next form of exchange is convective heat exchange, and so this occurs between an animal and the fluid that they're in, and that can either be air or water. In most cases, in most of our cases. And so we're talking about how these animals either lose energy to the surrounding environment or pick up energy from the surrounding environment, and ways that they moderate that exchange, right? So different types of organisms are going to have different factors that influence what they do, and we'll see that in just a minute. So of course the amount of convective energy, heat energy, depends on the temperature difference between what? Just make sure you're listening, because you know what happens if I think you're not listening.
The fluid of the animal.
The difference between the fluid and the animal, right? So if it's a big difference, high gradient, then there's rapid exchange either way, depending on the direction. The surface that is exposed, right? So if you open yourself up, like on a hot day, you're going to be kind of like stretching out because you're trying to get moving air, away from you. On a cold day, you're going to be doing that because you're trying to limit the amount of surface area that's available to lose heat, and so you're going to lose less heat that way. So the surface area that's exposed is going to have a big influence. And then the convective coefficient, and that depends on the size of the organism. And that relates to what I was talking about earlier in terms of the boundary layer. Okay, and so corresponding to that boundary layer is also the velocity of air movement around an organism, right? So if air is moving, then the boundary layer around the area of fluid that's not moving, which is the boundary layer, is going to be interrupted. If air is moving, that gets disrupted. If air is not moving, then it's not disrupted. So that can have some influence on heat exchange. And so, if we're talking about small organisms, that kind of corresponds to small boundary layers, right? So small organisms equals small boundary layer. So the small lizard is going to have an area of air around it, or if they're in water, that's going to be the same thing. So a small organism, you're going to have a relatively small boundary layer, and if that's the case, then it's not going to take a whole lot of energy to disrupt that, right? So if there's a little bit of air movement, then that boundary layer is going to be disrupted, and then the organism is going to be exposed to moving air. There's no boundary layer. So if you've got high temperature, low temperature, then this animal's going to lose energy pretty quickly, right, to the environment. So the size of the organism has an effect on their convective heat exchange because of this concept. If we're talking about a large organism, then that's going to be a large boundary layer. And so if we got, something like a monitor lizard, then the boundary layer is quite large. And so that, because it's so large, is going to take a greater amount of air movement to disrupt that, right? So if these two animals come out into the environment and air is only moving slightly, then that's going to affect this animal way differently than it will affect this animal, right? If the air is moving this much, then what's going to happen to that boundary layer? Nothing. And so, and because this boundary layer is still air that has some amount of energy in it, how that is exchanged with the organism is going to be affected by that, right? So if you have a boundary layer, then there's not going to be much exchange. If you don't have one, then there's going to be more exchange if everything else is the same. And so ultimately what's going to happen is that these two organisms have to do different things to regulate their body temperature as it relates to convective heat exchange. Does that make sense? So there's other things, of course, they can do, right? So if this small lizard wants to increase their temperature, there's a lot of things it can do that don't relate to convective heat exchange. But since we're just talking about that, I want to focus on that for now. So if we're talking about small organisms, they're going to do different things, right? So just imagine ground skink there, Skincella there, in the morning when they're trying to increase their body temperature so that they can get in their set point temperature range so they can be active, right? So they're going to come out from wherever they were hiding at night, and they're going to do some things to try to increase their body temperature. Does that make sense? Okay, so these guys, because their boundary layer is so small, then that's going to influence how quickly they can raise their body temperature, right? So if you're a little organism and you come out in the morning to bask in the sun, but you have a really tiny boundary layer and the air is moving at all, what's going to happen? What's that?
You're gonna get cold.
So you're basking in the sun and body temperature is going up, so the body temperature of this organism is going up, but the air is still relatively cool, and if it's moving, then you have low temperature, high temperature, and all that heat energy that they've absorbed through basking is just gonna get whisked away in the wind. And so this animal can't do that. It's gonna have to find a particular spot in order to use the solar radiation that it's absorbing from direct sunlight to increase body temperature. Otherwise, he's gonna lose it all through convective heat exchange. And so what these animals typically do is they will bask in the sun next to a large object. Why would they do that?
To stop the wind.
Not to stop the wind.
It bounces off of it. They're like a
No, it
rock.
doesn't bounce off of it.
Since it's a higher surface area than they do?
Huh?
Like the rock has more surface area than they do?
The rock has more surface area,
Maybe
but
they
the
like
rock is also a large object,
It has a
right?
larger bound.
A rock is a large object with a large boundary layer, which is an area of air that's what? Not
Just moving.
moving, right? So here's the rock. Around this rock is a boundary layer of air that's not moving. And so if this little lizard comes here and is now basking in the sunlight, but the air is not moving, then there's no convective heat loss. And so body temperature is gonna go up, and he's gonna be ready to go much quicker than it would be if he's basking up here on top of the rock, or not here on the top of the rock, but, you know, out here in the open where there's air moving. So all objects have a boundary layer, whether they're rock or an animal. And so this guy's gonna bask next to a large object so that he's not losing all the heat energy that they absorb through other mechanisms that we talked about already. Okay, so this is a lizard coming out in the morning. He's gonna sit on the rock, which has its own boundary layer, so air is not, and of course, the boundary layer could be disruptive, but what does that require? More energy, right? So wind. So if it's windy, it won't work. And so that's why, you know, when we go out looking for snakes, they're not basking out on a rock if it's really windy, because they can't increase their body temperature, because it's always just being whisked away with the wind because the boundary layer has been disrupted. But if there's no wind, then that's not the case. Okay, and so and then of course the other end of that is that at some point, if you're basking in the sun in the boundary layer of a large object, there's no air movement, at some point what's gonna happen? Your body temperature goes up, you hit that optimal range, it's still gonna go up if you don't do something about it. And so what these guys are gonna do is they're gonna move away. Now that the body temperature is high, they can afford to lose some of the heat energy through convective heat exchange, and so they can be active in different places. Okay, and here's an animal that is faced with that situation. So instead of going, retreating underground or in the hiding place, because that, now you're not active, you can't forage for food, you can't court mates and all that kind of stuff. So they're just gonna get away from the surface, and so he's up in the bush, right? So air's moving around up there, not so much close to the ground. Okay, so that's what small animals do. For large animals, it's different. To warm up, what would a large animal do in contrast to a small animal?
Move around.
So in the morning, so we're talking about a Gila monster, right? That's been in a burrow all night. Now in the morning, when they need to get their body temperature up to a point where they can be active, what are they gonna do?
Bask in the open.
They're gonna come up, they're gonna find a place to bask, and they're just gonna sit there, right? They don't have to search for a large object. How come?
They are.
Because they are a large object, and they have their own boundary layer. So all they have to do is come up and get out in the open, and are gonna be bombarded by solar radiation. Of course, again, if it's really windy, then the boundary layer is disrupted, and that's not gonna be effective. But under normal conditions, that would be the case. So a large animal's just gonna come out and bask in the open, and he doesn't have to seek a larger object because they carry their own large object with them. And so here's a large snake coming out of the burrow, just gonna lay out in the sun, using direct solar radiation to increase body temperature. On the other hand though, when this animal's body temperature gets too high, then they can't really do the things a little animal can do, right? So a small animal is gonna go up on the bush. A big animal may be able to get on the bush, but that's not gonna be effective. How come?
Still a large animal.
It's a large animal, still has that boundary, that pesky boundary layer that's following him around everywhere he goes, right? So going on the bush isn't gonna help because the boundary layer is still intact. And so these guys, essentially, at some point when their body temperature gets too hot, they're gonna just have to seek some other place to be that's cooler. Could be in the shade, could be in the burrow. So they're gonna have to shelter somewhere to get out of the sun. And of course, all of this depends on the environment that they're living in, right? So most temperate forest animals are gonna have a pretty easy go of it. They're just gonna go, in the shade, which could be right there next to them. So they might not have to go very far, but they do have to do something else other than get up off the surface. Okay, so convective heat exchange is important, more important for some organisms, and how they manage it is gonna depend on how big they are. And here's something. I think that's a big snake sitting in the shade. So they're managing their convective heat exchange. I saw a big king snake dead on the road yesterday, which was sad.
Oh.
Yeah, now at some point he was using probably conductive heat exchange, and unfortunately that's also where cars go, which is rare. I thought he was alive, he looked so alive. I got him out, when he didn't move, I thought he was dead, and I was like, well, he's still alive. I touched him and he didn't move. And it looked like he'd just been killed because he's still. Okay, so the next aspect is conductive heat exchange, and so this is the transfer of heat energy either from or to organism to the surface of an object. Okay, so not the same as the fluid around it, because surface, objects don't move like the fluid does, and so there's a little bit different. So it's particularly important for some organisms, especially nocturnal ones. Why would it be so important for nocturnal animals?
Because they don't have the sun.
They don't have the other mechanisms that diurnal animals have. There's no direct solar radiation, so they have to rely on indirect sources of heat energy to maintain their body temperature. So it could be quite important for these organisms. And so here the frog is basking on the road, like I said. And so the essentially idea is the road heats up and they can glean some heat energy from that. Major factors, of course, always going to be the difference in temperature between the organism and the object. That's true. Surface area, again, you can either try to maximize contact or minimize it depending on the objectives of the organism, the motivation. And so how that is managed depends on where the organisms live. So in forested habitats, typically what's happening is animals are going to move into a site that has sunny spots that they can absorb some direct solar radiation. But then they can also occupy places that were previously in the sun and have heated up, and so they can get some heat energy from that. Typically, when they're trying to raise their body temperature, they're maximizing contact between themselves and the object if the object has a higher temperature. So this is an example of an organism. So this is a desert species of lizard, and early in the morning the sun has warmed up the surface, and so it comes out from the burrow and just lays down on it. And so the more contact, the more difference there is in temperature, then heat energy is going to be transferred to that animal, going to get up to a certain body temperature and then be active, and then go do stuff. You go do lizard stuff. In desert habitats, generally, like I said, because there's such an abundant source of heat energy, they're mostly trying to manage how much of it is absorbed and trying to lessen that, because ultimately their body temperatures are going to be too high. So if you're going to increase your body temperature by maximizing contact, how do you lessen the transfer? You minimize the contact. And so a lot of desert species of lizards do this. So they move quickly, and then when they stop, they raise up their legs and they alternate back and forth. It's not because it's painful, right? They're not like when you walk across the blacktop at the beach, you're like, because it's painful. What they're trying to do is minimize the heat energy that they're absorbing. So they're running across and they're just picking up their feet. That's really all they can do, is just minimize that contact. The other option is to do what? Go underground, get out of the sun, be inactive, can't do anything. And so all this stuff, at some point they're not able to do it because there might be too much heat energy. They're going to have to be inactive, but that's letting them stay out a little bit longer, right? Which can give them a little bit more food, a little bit more mating opportunities, and of course that's subject to natural selection, and that's why these animals have come up with these strategies to do that. Okay, anybody have any questions on convective heat exchange? And so, or conductive heat exchange. And so, typically as herpetologists, we're looking for snakes and stuff. We go out in the evening as the air temperature is cool, but the road's still warm, and that's a good place to find snakes out basking on not basking, but sitting on the road. Unfortunately, that's also where cars drive, and so they get run over pretty regularly as a consequence. Okay, the other source of heat exchange, I guess, is evaporative cooling. And so this one's a little bit odd because most organisms aren't actively using evaporative cooling to manage their heat exchange. It's just something that will happen, and that has an influence on their thermal biology. And so, so we have to really kind of understand what's going on, because it is a part of their thermal biology. And so the basic idea is that as liquid H2O is converted to gaseous H2O, you're losing energy from that process, right? So I used to, when I taught freshman biology, essentially what you're doing is you've got water on the surface, and liquid water has molecules that are moving around at a rate. Right? whatever that is. As you add heat energy to it, what happens to those molecules? They move faster. And so at some point, they're moving fast enough so that some of them can come away from solution and into the atmosphere. And so the consequences of that, if you take away only the fastest molecules of H2O, what's the average speed of the rest of them? As you remove all the fastest ones? Slower, right? So on average, the speed is gonna be lower as he, right? So if you just take away all the fastest baseball players on the team, the average speed of the team is gonna get lower. And that's what happens. So the speed is lower, energy is lower, and what that allows is heat energy to be transferred from the organism into the fluid. And that's what we do essentially when we're sweating, right? So this water is becoming incrementally cooler. Transfer heat energy, heats up, water molecules get popped off, cooler, transfer energy, process just continues, and of course, this water gets smaller and smaller, and so if you don't replace it, what happens? You get dehydrated, which means you got the surface of the skin, and there's no real good way of transferring heat energy from the organism, and so that heat energy is you, and your body temperature goes up and up and up and up, and then you have heat exhaustion, heat stroke, right? So evaporative cooling is something that's going to happen if there's moisture in the air, or if there's moisture in the organism, or if the air and the organism are exchanging moisture in some way, that's going to impact their thermal biology. Okay, and so we're talking about evaporative cooling, right? So essentially, as this process is happening, you're losing heat energy, body temperature is going to decrease as a consequence of that. And so ultimately, it depends on the kind of organism you're talking about, but as that process continues, heat energy from the organism is going to be transferred first to the fluid, then to the atmosphere, so body temperature is going to drop. And so if you're trying to keep a high body temperature, then that could be a problem, right? If you're trying to keep low body temperature, then that's gonna work. It just depends on what the motivation is and what the consequences are. So we got 2 steps. First, you have to have liquid water that is in contact with the atmosphere. So the water has to be released into the atmosphere for there to be evaporation, right? So that's the first part of it. And then, of course, you've got the evaporation part of it. So as that water is converted to liquid gas or liquid water, then you have some kind of cooling effect. So if either one of those two, doesn't happen, then evaporative cooling is not very effective. And so if you think about the 2 different kinds of organisms, obviously it's going to have very different consequences because of the nature of one of the steps, right? Which step is different if we compare amphibians to reptiles?
It's the water loss, right? Because amphibians lose water toast.
Yeah, evaporation's not different. That happens automatically depending on the temperature, right? So the difference is the first part of it. Is water on the skin or not? If it's a reptile, what's the answer? No. If it's an amphibian, yeah. So if there's water on the surface, then it now is vulnerable to evaporation. So for amphibians, that process is going to be happening all the time. For reptiles, not so much, because they're covered with skin that doesn't allow water to pass through it, for the most part. And so for reptiles, evaporative cooling, not really a big deal. And so there's not a whole lot to talk about in terms of reptiles, although there are some situations where it's necessary. And so, of course, the metabolic heat prediction is pretty low as a consequence. So evaporative cooling, for the most part, that's going to kind of maintain general body temperature. So if the body temperature was optimal and the organism is respiring, their metabolic processes are happening about the same rate, so that water loss is not going to be very consequential to most reptiles under most conditions. So in some cases, animals have kind of, in particular environments that are going to give them very poor options, right? So you can either have a body temperature that's too high, or you can do something that takes you out of commission, essentially. Right? So some examples of that would be iguanas. Sometimes these guys and chuck walrus use the lining of the mouth essentially to allow for evaporative cooling to take place. And so their body temperatures are going up, they wanna drop that a little bit, so you can just open your mouth and expose the lining, which is moist, and then that's gonna allow, evaporative cooling to occur. Hold on one second. And so to increase that rate, you have to just increase the rate of respiration. What does that do?
What would you do?
Why?
Cause you're losing water every time you breathe or something.
Right, so when a dog is hot, they stick their tongue out and it's slobbery, so it's wet, so what's happening? Evaporative cooling is happening. So they don't just stick their tongue out, they also what?
Breathe.
They also pant. So the faster that's happening, you're moving air across that surface much more rapidly. And so if you just got your tongue hanging out, the air just sitting there, it's not really exchanging very effectively. But if you got air going back and forth like that, then that air is now exposing the liquid surface and evaporative cooling happens. Questions? Somebody had some questions. You had a question. Claire had a question? Yeah.
I wanted to ask, is this what's happening when crocodilians do the gaping behavior where they sit on?
Yes, I'm gonna get to that in just a second. Okay, so essentially what animals are doing is the first part, right, that we said is different for reptiles as compared to amphibians. They're getting liquid water exposed to the air somehow. When you breathe, that happens, of course, because air goes into your lungs, and the lungs are moist and it comes back out, and so you're gonna lose some water that way. Monitor lizards also do that. What they do is called gular fluttering. So gular region is the throat region. So what they do is they open their mouths, and this section right here is just fluttered. You know, it's like fluttery, 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 and that essentially does the same thing, right? It's just moving air, and so exposing air to that mucous membrane that's got moisture in it, and so that's ultimately how they're losing heat energy. They're also losing some water when they do that, but they're also cooling their body temperatures. The other example of that are crocodilians, and so not always will they do this, but particularly in some environments, and so these are Nile crocodiles, and so the reason why they're doing this behavior, which is called gaping, is the same reason. They're trying to cool themselves at least a little bit, right? So, and the reason why they're doing that is because they have two options as far as habitat goes. Here, just bombarded with solar radiation. Here, the river, which is cold. And so they've got two options, cold, hot. And so when they come out to bask, their body temperature is going to increase, but if they get back in the water temperature, their body temperature goes down too quickly. And so what they'll do is kind of a compromise. They're gaping. So they just open their mouths, exposing the buccal cavity to the air essentially, and that evaporates quickly because of the dry environment, and that also cools them. It also, again, they're losing some water that way, but they're also cooling their body temperatures, and so they can be more active for longer. They can increase their body temperatures. Okay. There's that. Okay, so for amphibians, it's more important just because of the fact that it's happening, right? It happens all the time. They can't do anything about it, at least the evaporation part from the skin, because their skin is porous to water. So they have highly permeable skin, and that allows for evaporation to happen very quickly. And as a consequence, that's going to take away heat energy, so it affects their body temperatures. And so at nighttime or in the shade, so many of these animals are active at night, but at nighttime there's no solar radiation and there's evaporative cooling, right? And so they're really having a tough time increasing their body temperature at night because you've got evaporative cooling all the time throughout all the body surfaces, and at the same time there's no direct solar radiation. So sometimes at night their body temperature is lower than the measured air temperature in a still environment. So because they're constantly losing heat energy through evaporative cooling. In the daytime, they're limited in what they can do. Their body temperatures can't get very high, right? Because as their body temperature goes up, evaporative cooling is going to be prominent always, and so that's going to allow them to lose heat energy. So body temperature goes up because they're in the sunlight, but then evaporative cooling through all the surfaces is going to allow their body temperatures to cool. And so their body temperatures can never get high until what happens? When does cooling stop? When they run out of water. And for an amphibian, obviously that's gonna be a serious issue, right? So their body temperatures can't get real high because they're constantly losing heat through evaporative cooling. The only way that'll stop is if you stop the transfer of water into gaseous water. And that won't happen for an amphibian ever until they're completely dry, right? Because their skin is always exposed and permeable. And so the evaporative cooling is gonna always be an influence. So if we think about, if we compare, amphibians and reptiles, generally their body temperatures are gonna be lower. They're active at lower body temperatures, and metabolism is lower than reptiles, because reptiles have that skin that prevents that from happening. They can get their body temperatures way up. They can get it too high when the proteins start getting denatured, and they'll die, but they're not dry. They still got plenty of fluid inside the tissues. Okay, so some of the strategies for animals and that live in particular environments, like lithobates, which are bullfrogs, bronze frogs, leopard frogs, those guys. A lot of times they're in permanent bodies of water, and so they'll get their body temperatures up as high as they can by basking in the sunlight, but still be in the water, right? And so I think I have a picture. And so the basic idea is as the water evaporates and cools them, they're still out in the sunlight. So their body temperature is as high as it can go if they're basking in the sunlight. If they get out of the sunlight, then they're still gonna have evaporative cooling, and their body temperature is gonna get lower. And so that's about as best as they can do. They can sit in water and bask in the sunlight at the same time, get their body temperatures up at higher body temperatures. And so generally amphibians are gonna operate at much lower body temperatures than reptiles do. Okay, does anybody have any questions? All those things. So the idea, right, is that these animals are trying to get their body temperatures to a certain range, and all of these environmental factors play into how they do it. And their behavior kind of depends on the circumstances and the nature of the organism, the size of the organism, all those things that influence how heat energy is exchanged with the organism. The other thing I want to talk about is the kind of the behavioral components of that, right? So if we're thinking about thermoregulation, maintaining a body temperature at a certain range, it has to come along with other factors other than just how heat is exchanged. And so I want to kind of get into that a little bit. So most amphibians and reptiles are thermoregulators most of the time, right? So they're maintaining their body temperature within this range. That's when everything works best, and that's what they're trying to do. And that, of course, that idea is related to the set point temperature range that we talked about. And so typically when they're active, they're trying to do that. They're trying to maintain their body temperature to do that. So as body temperature moves out of that, then they have to do something different, right? They have to make some adjustments. If their body temperature is too low, what are they gonna do? I caught you right in the middle of it. So when their body temperature starts to get out of that, if it gets out of that in the low end, what's an animal gonna do? How?
To the sun.
Could be sitting in the sun. What else could it do?
Laying on the road.
Could lay on the road. What else could it do?
Lay on a rock.
It could lay on a rock, which is similar to laying on a road. Or if it's already out, it could turn itself sideways to get more, or it can make itself darker. All those things that we talked about that increase body temperature, they can do all those things, right? Depending on the circumstances. So just some examples. They're gonna move to the sun to bask. They might move to a rock that's hot. They might darken the skin. They might change their orientation so that they're absorbing more solar radiation. So a lot of things they can do if their body temperature is too low and it's not in the set point temperature range. If it's too high, if it starts to get out of the set point temperature range on the other end of the scale, what do? Yeah, how? They just cool off. The opposite of all those things. They go in a hole, they turn perpendicular to the sun so that they're just on their face, and so they can still be, they lift up their legs like that. I can't do it, can I? This one? Yeah, they do lift up their legs. That's not hard to do. Does that do it? Yeah, lift up their legs to reduce that. So all those things that we talked about, that they're trying to minimize heat exchange. They might, if it's too high, they might pant. They might gape, they might do all those things, you know, that they can possibly do. So the control of that is governed by part of the brain, their thermoregulatory system. And so, you know, their behavior often affects, or is affected by the temperature of the head, essentially. So, because that stimulates the hypothalamus. Okay, so the couple of things about the set point temperature range is not always the same for every species. It's typically species specific, right? So if you measure different species, you're gonna find different set point temperature range. It's not necessarily different, but many species have different temperature ranges that they work best in. It's influenced by different things. It can be influenced by sex, but that's variable, right? So in some cases, males have higher, females have lower. In other species, females have higher, males have lower. So within a species, there's some patterns related to sex, but depends on the species. Reproductive status, it is different. So typically, if a female is gravid, then, gravid, I guess, their body temperature is a little bit higher, which increases, you know, development and all the things, the physiological things that go along with, proteins being deposited in the ova, et cetera. Digestive requirements, again, so typically if an animal has recently eaten a meal, body temperature does what? Or preferred body temperature does what? It goes up because metabolism is increased and that helps to digest the food particles much quicker. The health is impacted, or the set point temperature range is influenced by the health. Typically, what would you expect? If an animal is ill, what would you expect to happen to the temperature range? Higher, right? And so what happens to us when we get sick? Our temperature goes up. If you're an animal that doesn't have physiological mechanisms, because you want stuff to happen faster, including the immune responses, you want that to get going. You don't want to go, hey, we'll take care of that in a minute. You want it to happen now, right? So for these animals, they're gonna try to bump their body temperature up, yeah.
Oh, so when they're ill, they're gonna try to bump their body temperature?
Yeah, there might be some behavioral adjustments. So, animals, it's been documented, I think, with snake fungal disease, tend to come out and bask more, and more frequently, sometimes even during the winter. If it's warm, they'll come out and try to increase their body temperature just in response to it.
I thought you were saying they're ready to fever like we
They don't have that, right?
Okay.
They don't have internal heat producing mechanism physiologically, but behaviorally, they can make adjustments to try to increase their temperature.
Mhm.
And so that becomes their preferred body temperature, right? So if you measured a sick animal, put them in a gradient, they're gonna seek a range that's higher than a healthy animal would.
And is it that fungal on the scales that we saw on the snake?
Snake fungal disease?
Yeah, I wonder if the sun doesn't help just like dry that up too.
No.
No?
No, the sun by itself doesn't have an effect on the fungus.
Just the heat.
It's just the heat is gonna have an effect on the immune system of the animal, help it rid of the fungus. Okay, season can be different as well. So some animals are gonna do different things. Not obviously in the summertime, the environmental temperature is higher, but the preferred body temperature can also change according to the season. Okay, so those are some aspects to it. And then the other thing I want to talk about is the other factors that influence what an organism is doing as it relates to thermal biology. Because we're talking about the animal functions best physiologically at this range, but that range is not always available. And so you have to do something different, right? To maximize your overall fitness, essentially, is what it boils down to. Okay, so as we talked about before, just the physiology of the organism is going to be maximized at certain temperatures. That's what we talked about with set point temperature range. Everything works best at a particular temperature, but they may not be able to do that, right? So depending on the circumstances, they might not be able to get to that temperature for a variety of reasons. And so some of the things that are associated with that. So what I'm getting at here, so if you're an animal and you're getting yourself into this optimal range, what are the costs associated with that? Or what can be some costs? It might be reduced foraging success. If the prey that are optimal are not available at that temperature. And I'll talk about some examples of that in a minute. So some of the things that you eat might influence your body temperature availability. You also might have lower reproductive success, right? So in other words, if you get into this range, that might take you out of the running for courtship, as an example. Because courtship and physiology are not necessarily always linked together. You also might be at a higher risk of predation, right? So if, for example, if you're a lizard, your body temperature goes up, you wanna cool off, you go out on a bush to take advantage of convective heat loss so that you can remain in optimal body temperature, what now is also true. Yeah, a hawk's gonna swoop down and pull you off the bush and you're gonna be, you're not gonna be successful anymore. So the other option is to not go on the bush, which takes you out of optimal body temperature, right? So the thermal biology is not by itself, it's not in a vacuum. And so the cost, of course, of going outside of that, right? So now our other option is to not be in the optimal body temperature. And so there's some costs associated with that. And so typically it's gonna be, because it's physiology, right? So we're talking about physiological processes, and that happens best at your optimum body temperature. If you're outside of that, then those things don't happen very well, right? So they don't happen effectively. And so that mostly boils down to some type of performance. It could be your escape response, right? So the time it takes you to recognize a threat and then avoid it, that can be lessened, and so, or increase, I guess, the time. Sprint speed can be influenced by that. Endurance can be influenced by that. And one of my friends in graduate school, he was studying garter snakes was his model, and he was studying their sprint speed and endurance. And he essentially put them on this little track they couldn't get out of, and he would tickle their butts with like a bottle brush and just chase them around the track until they stopped moving. At some point they give up, they stop. And so he was looking at genetic stuff. But if your body temperature is too high, your endurance is lower. Or if your body temperature is too low, your endurance is lower, or your sprint speed is lower. So it affects your physiological mechanisms that ultimately affect how you move, how you perceive what's going on in the environment, which then opens you up to a lot of other things, mostly predators, right? Or competition's not as strong. So ultimately, if you're outside of that, some physiological processes are going to be inhibited. And then of course, it might actually expose you to lethal temperatures. Right? So if you're outside the body temperature for whatever reason, you might have temperatures that are either too hot or too cold that will actually kill your organism. And so those are some of the costs associated with being outside of body temperature. So what I want to do to kind of show you that is to give you some examples, and so you can see how optimal body temperature is influenced by other things. And so I have 3 examples to share with you. So the desert lizard, Scoloporus mariami, is a species that's in the same genus as our fence lizards. This is just a picture of the animal. And so these animals in the morning time, they're active and their body temperature is about 33 degrees Celsius, so pretty high body temperatures. They're active at very high body temperatures. They're inactive during the midday period because they're desert animals, and so during the midday, the air temperature and all the other surfaces are just too hot for them to be active. They can't really rid themselves of body heat enough. And then the evening, they're active again at slightly higher body temperature, so 37 degrees Celsius is their active. Okay, and so through experiment, researchers have shown that they're at these higher body temperatures, their performance is reduced. So when their body temperature is at 37 degrees Celsius, some of the things I talked about, endurance, sprint speed, all those things are inhibited. So they don't function as well as an animal that is 33 degrees Celsius. So that's essentially their optimal body temperature is 33. But in the evening, they're active. They're very active, even though their body temperature is well outside their preferred body temperature range. And then the reason for that is because being active at that time is going to influence your mating success. So the females of these animals are going to be kind of hiding out in microenvironments with lower air temperatures. So the females are hovering around 33 degrees Celsius. But the males, in order to get access to a female, they have to court. And the female is going to choose which male she likes best based on their courtship behavior. To do that, they have to be out in the open and showing off in front of the female. While they're doing that, their body temperature is well outside their optimal body temperature. So the choices are to do that and expose themselves to body temperatures that could be lethal to them, or at least, you know, harmful in terms of their response, or not mate. And so obviously, you know, the mating instinct is pretty strong, otherwise you wouldn't see the species. And so this really only applies to the males. The females tend to stay in microclimates that don't let their body temperatures get outside of that set point temperature range. And so the idea here is that even though their body temperature is well outside their physiological preference, they're still doing it, and that's to get access to mate with the females. Okay, like I said, so the cost, so suboptimal just means not too cold, but outside of optimum. And so that being outside that range is outweighed by the mating success that they're going to achieve if they are successful in mating with the female. And the males that don't do that aren't successful, so they don't get passed on to the next generation. Okay, so that's one example. The other example I was going to share with you, I'll wait until next time. Okay. Does anybody have any questions?
I do.
Okay.
Do you know what our final exam is?
Your final exam?